This lecture will introduce data assimilation, mainly focusing on concepts, procedure, and applications. Again, I'm Ichi Lu, a professor from Cornell University. Data assimilation is a statistically rigorous approach to model parameterization. The latter is one of the three essential elements towards a realistic model prediction. To realistically predict the ecosystem response to climate change, we need the model structure to represent the real-world processes that control system functions. We also need model specification through parameter estimation to constrain model predictions. Moreover, the external forcing variables have to reflect the physical, chemical, and biological environment that an ecosystem experiences to perform its functioning. Ideally, all the three elements have to be perfectly aligned before a model can well predict ecosystem responses. In reality, we spend much more time to develop process-based models than thinking about parameterization or forcing. When prediction of a model does not match with observations well, we usually look only at the model structure and often ignore more parameterization or forcing. In fact, we have been running tuning parameters for several decades but did not learn much from it. Now, data assimilation is an approach that can be used to rigorously estimate parameters and offer a new way to learn about model parameterization. We will learn about data assimilation in most of the units 6 to 10. To have realistic external forcing variables to drive a model, we need to have data model consistent systems which can be realized by interactive ecological platform for assimilating data, so-called EcoPad. So these lectures mainly about the data assimilation to parameter values. Data assimilation is a statistical approach to optimally combine models with observations. The utilities of data assimilation include estimation of parameter values of a model, quantification of model uncertainty, select of alternative model structures, and evaluates values of different data sets to constrain model predictions. Now let's go back to modeling in a traditional sense. Traditional modeling is often called simulation modeling or forward modeling. Simulation modeling usually needs to develop a model first. The model usually means model structures with a series of equations to represent a process in a system. Then we're using forcing variables to drive a model. The forcing variables for an ecological model usually include radiation, temperatures, and precipitation. When the forcing variables are used to drive a model, the model generates outputs such as carbon storage or net ecosystem exchange. The model outputs sometimes are compared with data for validation. This simulation approach has extensively used by ecologists for about 60 years. It is powerful for exploring ideas and hypotheses in ecology, Most often, the simulation model cannot effectively used for prediction or forecasting. Here is an example of a simulation modeling study done at a free air CO2 enrichment phase project in Duke Forest. The photo shows 3 phase rings, 3 control rings, plus 1 prototype ring. In the phase rings, the CO2 concentration was 200 parts per million, higher than that in the 3 ambient rings. One of the ideas for a phase study was to show how a forest would be when CO2 concentration increases to the elevated level in middle of this century. That is, the hypothesis was that forest carbon sequestration in elevated CO2 ring will be the estimate when the atmospheric CO2 concentration was gradually increasing to that level. At that time, I was collaborating with Jim Reynolds to test this hypothesis using a simulation modeling approach. We used a terrestrial carbon sequestration model, a precursor of a TICO model, to test the hypothesis. We simulated 2 scenarios. One was to have CO2 concentration gradually increasing as shown in panel A, or abruptly increased as in panel D. When atmospheric CO2 concentration is gradually increasing, both photosynthesis and ecosystem respiration are gradually increasing as shown in panel B. But the respiration lags behind due to the carbon that enter the ecosystem through photosynthesis have to stay in the ecosystem for a while before it is released by respiration. The differences between photosynthesis and respiration is the ecosystem carbon sequestration, as shown in panel C. The modeled carbon sequestration gradually increasing under the gradual CO2 increase scenarios in real world. In contrast, photosynthesis abruptly increases in response to a step increasing in CO2 concentration as in the phase experiment, but the ecosystem respiration gradually increasing lead to a pause increasing in carbon sequestration, followed by gradual decline as shown in panel F. This is a simulation modeling study. It is quite powerful to falsify the original hypothesis that carbon sequestration observed in phase plots can be extrapolated to real world when CO2 concentration is gradually increasing. However, when simulation models are used for prediction or forecasting, the model and the data usually do not match well. This figure shows predictions of soil carbon density by 11 models used in the coupled model intercomparison project phase 5, CMIP5, on y-axis versus observation-based carbon density from homogenized wood soil carbon database HWSD on x-axis. None of the model predictions match with observation well. The bad match between the models and the observations are partly due to the no data constraints on model structures or parameterization. Data assimilation is an approach to combine models with data to improve model prediction and forecasting. Data assimilation is sometimes called data model fusion, inverse analysis, inverse modeling, multiple constraints, or inference analysis. Depends on the situations when this technique is applied. Modeling is one approach to scientific inquiry, mainly through process thinking. Data are obtained from field or laboratory research, which also approach to scientific inquiry through snapshot the state of ecosystems at the time when the observation was made. The two approaches acquire information on different aspects of an ecosystem. One is through recording the states of the ecosystem, the other is through process understanding. Integration of a model and the data will help gain the best knowledge from imperfect data and imperfect model. Data assimilation is one of the approaches to integration of data and model. It starts with data and associated uncertainties or noises. The model is combined with the data is combined with modeled value to inversely infer model structures or parameter values. So data assimilation is also sometimes called inverse analysis or inference. Now let's explain procedure of data assimilation. To help learn about the procedure of data assimilation, we may examine how we conduct a regression analysis. When we study a relationship between arm length versus height, for example, we usually have to go through 7 steps. First, we need to decide what the objective is. In this case, we try to predict height from arm length. Second, we need to collect the data of arm length and height for a population we are going to study. Third, we need to select a regression equations. In this case, a linear model is adequate. Fourth, we need to measure mismatches between observed heights y and estimate heights from a regression line y hat. Fifth, we will minimize the mismatch using a method of the least squares. Sixth, we will obtain the optimized estimates of regression coefficients a and b. The 7th step is to predict your height from your arm length. The figure on the right side of the slide shows the regression line between height and arm length from a sample in Nigeria, reported from a paper by Vendejax and colleagues in 2001. In short, the 7th step of conducting a regression analysis are: set up an objective, collecting data, selecting an equation, measure mismatch, optimization by minimizing the least squares, estimation of parameters, and predictions. These 7 steps of procedure can be similarly used for data assimilation. To conduct a data assimilation study, we also need to firstly set up an objective, such as predicting ecosystem responses to global change. Secondly, have data sets. Thirdly, have a model. Fourthly, develop a cost function to measure mismatches between observations and model values. Fifthly, have a global optimization to minimize the cost function. Sixthly, estimate the parameter value. And seventhly, do prediction. I'll describe this 7-step procedure for conducting data assimilation, mainly using the example in the study by Xu Tao. Please have the paper with you, as you might go back and forth between this lecture and the paper. Some new concepts, such as the mapping function, Markov chain Monte Carlo sampling series, and the metropolis criteria, will be explained in lecture 6.2 and practice. You will go through all the 7 steps in the practice session in Unit 6. Step 1 is to define objective. The general objective of this study is to predict ecosystem responses to elevated CO2 concentration with uncertainty quantified. You can find this objective in paragraph 2 on page 1. Notes, all the page numbers, figure numbers, etc. are referred to those in Xu et al. Paper. A more specific objective of this study is to estimate parameters C1 to C7 in Table 1 on page 3, and then predict a carbon pool change at ambient elevated CO2 treatment in Duke Forest, as described in paragraph 4 on page 2. You may pause if you need more time to read those paragraphs. Step 2 is to have data sets. The 6 data sets used in the study are soil respiration, woody biomass, foliage biomass, little fall, soil carbon, and mineral carbon at ambient and elevated CO2 treatments. Those data sets are described in paragraph 6 on page 3 and table 2 on page 4. We also need to use standard deviations of the 6 data sets in data assimilation. Step 3 is to have a model. This study used the terrestrial ecosystem TECO model. The TECO model depicted in figure 1 and described in equation 1 on page 2. Please note that figure 1 has a typo. Pool X1 should be non-woody pool, which include foliage and fine root biomass. One more point is that the TECO model in this paper was described by metric equation, which is the same equations as we studied in units 1 to 5, with slightly different notations. Step 4 is to define a cost function. The cost function is to measure mismatches between observed and the modeled value. The mismatches are described by equation 5 for individual data sets and equation 6 for all the 6 data sets on page 4. The modeled value have to be mapped to the observations by mapping function theta, which has 6 elements respectively for 6 data sets, are described in equation 3 on page 4. The mapping function will be further illustrated in practice session in Unit 6. The cost function is equivalent to likelihood function in equation 8 on page 4. Once we have defined the cost function, now we need to minimize the cost function by global optimization in step 5. The optimization is done with a Markov chain Monte Carlo sampling series. The MCMC has two phases, proposing phase and moving phase. The proposing phase is to generate a new parameter sets. The moving phase is to examine if the newly proposed parameters should be accepted or not using the Metropolis-Hastings criterion. The two phases of MCMC are described in paragraphs 12 and 13 on pages 4 and 5. The study used 5 parallel runs to test convergency of a sampling series with the Gilman-Rabin method, as described in paragraphs 14 and 15 on page 5. After cost function is minimized with global optimization using the MCMC method, we obtained estimated parameter values in step 6. The estimated parameter values are described in paragraph 17 on page 5, depicted in figures 3 and 4 and table 3 on pages 6 to 8. Estimated parameters have 3 types of distributions or histograms as shown in middle column in figures 3 and 4. The 3 types of histograms are bear-shaped for parameters C1, C3, and C4, edge-hittings for C6, and flat for C3, C5, and C7 in figures 4 on page 7. The bear-shaped histograms means that those parameters are well estimated. The flat-shaped histograms means that those parameters are not constrained. In other words, the 6 data sets we used do not have any information that is related to those parameters. The edge-hitting histograms means that those parameters are strongly correlated with other parameters or caused by other reasons. The estimated parameters in step 6 will be used in the TCO model to predict the ecosystem responses to elevated CO2 in step 7. The predicted carbon pool change in year 2010 at ambient and elevated CO2 are described in paragraph 17 on page 5, figure 9 on page 11, table 4 on page 12. Uncertainties in model prediction is quantified with cumulative density function in figure 9 and confidence intervals in table 4. CO2 effects are represented by the predicted change in pool size as indicated by the differences between the solid line at elevated CO2 and the dashed lines at ambient CO2 in figure 9. As you can see from the paper, elevated CO2 have the largest effect on wood biomass but no effect on passive soil carbon pool. Again, the 7 steps to conduct a assimilation study are setting up an objective, collecting data sets, having a model, define a cost function, use a global optimization method to minimize the cost function, estimating parameter values, and predicting. The 7-step model data assimilation is essential to estimate the parameter values and then constrain model predictions through parameterization. The parameterization in turn is essential towards a realistic prediction. Now I'll use one example to illustrate how data assimilation can be applied to ecological study. We have applied data assimilation to evaluate whether a soil priming effect lead to net loss of soil organic carbon by adding new carbon input. The study was done by Junyi Liang to test 4 alternative model structures with 84 data sets from 26 studies with isotope labeled carbon addition treatments. we need to define what is the priming effect is. Priming is a term to describe stimulations of old soil organic carbon decomposition by new carbon addition. This priming effect usually results from stimulated microbial growth by new carbon addition. The study required data to be collected from isotope-labeled carbon addition experiment. Those studies have to provide SOC content, the added new carbon amounts, multiple measurements of CO2 emission rates from old soil organic carbon, and the amount of new carbon substrate added. In total, the study used 84 data sets from 26 publications. The study used 4 models, including conventional soil organic carbon dynamic model, new old carbon interactive model, Michelson-Menten models, and reverse Michelson-Menten models. The study first tested the 4 models by comparing observed with modeled cumulative CO2 emission rates. The observed rates are represented by dots and the modeled value by line and the shaded area. The black dots, black line, and the shaded area are for carbon released from a newly added carbon. The red dot, the red line, and the red shaded area are for the total carbon released from soil incubation. The purple dots, purple line, and the purple shaded area are for carbon released from old soil SOC. The conventional model can fit observed soil carbon release from new, old, and total SOC extremely well. The interactive model can fit observation quite well too. However, the fitting is not that good for Michelson-Menten or reversed Michelson-Menten models, especially when observed carbon release from old and total SOC. The model data fitting also shown in panel A to D. Conventional model fits the best, Michelson-Menten model fits the worst. Junyi Liang used the deviance information criteria, DIC, to select alternative model structures. DIC penalized the model severely by number of the parameter. Among the 4 models, DIC is the smallest for the interactive models but largest for conventional models, as the latter has 12 parameters, although the fitting of the model with the data is the tightest. Based on the DIC, the most likely model is the interactive model. We use the interactive model to estimate the priming effect, replenishment, and the net change in carbon after adding new carbon to the soil incubation experiments. This figure showed that nearly 54% of newly added carbon stays in soil, stimulated old carbon decomposition by priming effect is nearly 10% of newly added carbon. As a consequence, SOC has the net gain of 33% of added new carbon. This analysis indicates that priming does happen, but unlikely lead to a net loss of SOC. The priming effect varies with the nitrogen concentration of added new carbon substrate. If added new carbon is purely sugar without any nitrogen, the priming effect is the strongest and the net carbon gain is the smallest. If added new substrates are leaf litter with more nitrogen content. The priming effect is the smallest and the net carbon gain is the highest from added substrate. This study used the data assimilation to address a highly controversial issue on priming effect. The study showed that adding new carbon to soil does result in priming effect, but eventually lead to net carbon gain by 33%. The increased SOC is related to nitrogen content in the added substrate. The less nitrogen the substrate has, the stronger the priming effect is, the less carbon gain in SOC. The study also suggests that two-pool interactive model is the simplest, most parsimonious model to represent SOC priming effect. Overall, data assimilation is a statistically rigorous approach to model parameterization, which is essential to generate realistic model prediction. And data assimilation also can test the alternative model structures as illustrated by the last examples. Data assimilation is usually conducted in 7 steps, and I used one example to illustrate the data assimilation can be used to estimate parameters, select alternative model structures, and quantify uncertainties in model predictions. Thank you very much for your studying the lectures.